Good morning. I think we have pretty close to a normal voice today. The first thing I wanted to do is point out to you that in Chapter 9, I should have done this earlier, there is one section that we're not going to take. It's not very long, but it's called Personal Probability. And as you can see, it's on pages 239 to 240. Just take a quick look at it. Honestly, its inclusion here is kind of strange, because what it amounts to is this is a section where you assign your own personal judgment on things, not a whole lot of value when you're learning probability. So it's like saying, yeah, I think he's got about a 3 out of 10 chance. Okay, we're not going to be doing that section. And there is one problem from the assignment that kind of is linked with it, and that's number 923. So even though I won't mention this later, you're going to have to remember that I think I say 1 to 51 odds. Well, drop that one, okay? So first, that's the first thing we needed to talk about today. Try to wrap up Chapter 9 today. Is that a density curve? That red curve? Do you remember the way to find out? Adds up to 1? Can you tell me a little more what you mean by adds up to?
The area.
If the area under the curve is 1, yeah. Is that the case here? We have, I think you would agree, a triangle. Okay, got to remember, how do you find the area of a triangle? 1/2 times base times height. The base here is 2. The height, I don't know if you can see it real well, on the right there is 1. 2 times 1 is 2, and half of that is 1. So yeah, this is a density curve because it has an area of 1. Okay. Good question to get us back into this. Verify by geometry. Well, we just did that. Part B. What's the probability that using this density curve that will have a value less than 1? Okay, now what you need to do in order to answer a question like this is kind of mark right on the drawing. So I'm having strange results today. Sorry about this. Let's see if I can do it with a mouse. Make a line in here, and then using, and just shade this in. Except I whiffed there. Okay, less than 1 would be this part that I've shaded in. Okay, so the probability that we're going to be less than 1 is the area of that shaded region, which would be what? Base times height divided by 2 again. This time the base is 1, the height is 1. 1 times 1 is 1, half of that's a half. So you have a 50% chance that we're going to be less than 1. How about the part C? What are our chances of being less than 0.5? Excuse me. Well, now, I don't know if I got that pretty close. Now we just want the area of this shaded curve. My shading is pretty bad. I'm trying to do this with a mouse because for whatever reason my wireless thing is working kind of strange today. What's the area of that curve, or that part, shaded area? Base, half. Height, looks like it's a half. What's a half times a half? A fourth. And then half of that is an eighth. So the chances of being less than 0.5 appear to be 1 out of 8. So on a density, so the cool thing about a density curve is you can use it to actually calculate probabilities. So, I mean, there might be a question like that on the exam where I give you a density curve, and then I say to you, using the curve, find the probability that the variable is greater than 1.5, or like we just did, less than 0.5. And then you literally go on the graph, shade that area in, okay, figure out the area. So does that mean you have to have tons of area formulas memorized? No. I would say, I mean, some pretty obvious ones. Rectangles, triangles. I wouldn't worry about a lot of others. Okay, then you're going to come upon some familiar creatures called normal probability models. And I thought we'd work through an example together that we should bring this back in your head. There's also a little bit of new language here, terminology, notation. You will find this on page 237 in your books. Just flip back a page. Example 9.9 is pretty much in the center. It says, what's the probability that a randomly chosen young woman has height between 68 and 70 inches? And of course, we wouldn't be able to do that if that's where that ended. They had to tell us something about it. They said the height x of the woman we choose has, remember what that notation is? A normal distribution with a mean of 64 inches and a standard deviation of 2.7. So right off the bat, we can use our normal curve and everything we learned in the past about that. So I started sketching in the mean. I put that at the central mark, and then on each notch I went up 2.7, or going to the left I went down 2.7. So you guys remember how to do that. Now, do you see this notation in the book? At P, parentheses, all that's the math way of saying what's the probability that x is between 68 and 70 inclusive. By inclusive, I mean, notice it's not just between 68 and 70, but including the endpoints. Well, I don't know if you remember what we have to do, but we got to find the z-scores for 68 and for 70. And then we got to find the probabilities for those two, and then literally subtract them. So, threw a table in here. First, we need our little z formula, right? Let's see if I can do this. Sorry. I don't know, this thing's really hyper today. Okay, you should remember that formula. In this case, we're going to use what? The 68 first of all, minus the mean, divided by the standard deviation. So, you got to do a 4 divided by 6.7. Thanks. $1.48 approximately. Okay, and we're going to look up the probability for that, but why don't we do the other one right away? Our, I guess we'll call this Z1, and for our second one, this time we're using, what is it, 70? 70-inch limit on the top. This time we have 6 over 2.7. And this time we get 2.22, approximately. Okay, so now what we need to do is look up the probabilities for those two. Remember our reasoning. We haven't done this for a while, but if we find, remember the table always gives you everything to the left. So if we find everything to the left of 70, and we find everything to the left of 68, if we subtract the probability of 68 from 70, we'll get rid of all that excess that's off to the left. You follow? You know, you got all of this minus all of this, and it's going to give you just what we want. So, table, I think I've got one in here. Yep. Okay, what was that? 1.48 z-score. So let's start with that. Looks like 0.9306. Let's jot that down. Okay, and then let's do 2.22. Probably should have done that one first, but that's okay. 2.22. 0.9868. Subtract. And it looks like the probability of being between those two is about 5.6%. So the cool news is you've done this before. But I wanted to kind of refresh that because this is still one of the most common probability models, especially when it comes to anything naturally occurring. And it fits because the total under this normal distribution curve is 1. If we don't have a total area under the curve of 1, then we can't use it. But so this works. Okay. Now, I don't quite know why I put this in there. I just thought it was an interesting, kind of weird, trivial statistic. I probably have shown you that before. They always talk about the Windy City, Chicago. It's not very well earned. They're only, what, like 16th in rank? I mean, really, we should call Great Falls the Windy City. But that just doesn't sound right? Notice we made the list too, Milwaukee. So even we are a windier city than Chicago. Anyway, I thought that was kind of interesting. Some kind of, I don't know when this was taken. Maybe it needs to be updated. Anyway, just kind of a little entertainment fact. Okay, now, a really unique principle I need to show you about today called Benfords Law. Benfords Law. And it has to do with numbering that we use for whatever we do. Pick up a newspaper and grab the numbers in the paper. Scores, weather. Pick up an accountant's ledger book, and they will use things like account numbers and money numbers. What else can you think of that has numbers? I mean, just anything you pick up. And I'm going to show you a variety of those in a little while. So these are non-random now. They're numbers that we generate for certain purpose. Oh, here's another one. When you get a checkbook, you get check numbers. And you can even request where you'd like your check number to begin. Usually you like to begin not at 1 because, or, 001 because then everybody knows you're kind of new at it and they might not trust you as well. So you can request to begin your checks at some other number. But anyway, you got all these numbers everywhere. They're not random, but they're you pick up an encyclopedic book that has I don't know, the average wind speeds in cities or the average current rates on rivers. Whatever it may be, this is totally wild. Benford discovered what he called Benfords Law. And it's used to help spot fake numbers. Fake numbers as in somebody wants to do some cheating and put some fake entries in an accounting book. or um, submits a fake check. Okay, well, Benford found out that when you use real things, there's a ratio of numbers that appear, and it's in this chart. You notice that 1 appears by far the most. So in other words, first off, you notice these are not random, because if they were random, everything would have a chance of, an equal chance of being chosen. And these bars would be flat and would be constant. Notice 1 has the greatest chance, 2 has the next greatest chance. By the way, 1 has a chance of about 28%. Well, here's the actual number. 30% of 1 being in there. Then it goes down to 17.6% for a 2, a 3, 12.5, all the way down to a 9.04, 4%. Okay, why is that? Well, I'm sure it's partly because most numbers are actually counts of things, and where do we begin counting? We begin counting at 1. And even if you start your checks at 10,000, it's going to be 10,001, 10,002. And if you don't count real far, you never get up to the higher, I don't know. That's the only thing I can think of. Okay. So here it is. It says fake numbers in tax returns, payment records, invoices, expense account claims, and many other settings often display patterns that aren't present in legitimate records. Some patterns, like too many round numbers, are obvious and easily avoided by a clever crook. Others are more subtle. It is a striking fact that the first digits of numbers in legitimate records often follow a distribution known as Benfords Law. And I don't know, it's kind of a shock, isn't it? You'd think there'd be some kind of an equal distribution. Way at the bottom, Benford's Law allows easy detection of phony financial records that have been based on randomly generated numbers. So one thing that modern-day accountants often use as they're doing their audits is they will use Benford's Law. Just a comparison again, if numbers were truly random and the numbers 1 through 9 were the only numbers that were used, then each number would have a 1 out of 9 chance, right? They'd be all equal. It'd be equal chance of everything being picked, like in an SRS. But real first digits follow Benford's Law on the bottom. There's quite a change here, and so this isn't that terribly hard to spot. Here's what's wild is this: the sources can be anything, as this figure shows. In blue, I don't know if you can see the far left dark blue bars. That's Benford's Law. Next one over, the second bar is newspapers. Just pick up newspapers and look at the numbers that appear. Third one over is the 1990 census. The last one is Dow Jones. Just picking stock quotes. Okay. And you notice they follow the pattern quite well. Now, here's just an example. Benford's Law, again in blue. This next bar is true tax data, taken off of true taxes returns. Here's some fraudulent data. See how bad it is? Look at that bar in the center for 5. It's just like obvious that somebody faked this. It's not even like I think. This one just like whacks you right in the face. You see how different the graph is? This person seemed, in fact, interesting. I don't know why they were so heavy on 5 and 6, but notice they have almost no ones. And of course, that should be the most common. Here's random guess data, just literally using a true random number generator, and you see how even that's pretty obviously different from Benford's Law. So if somebody said, you know, hey, we're going to fake these financial records, we're going to use a computer to pick out random numbers, even that won't work. Very interesting. I don't know, the first time I saw this, I thought, no, this can't be true. It just doesn't, it's pretty amazing how this works. Just to show you how many different kinds of things this fits. If you could just take a look at this column here, I'm just going to read through the totally bizarre list of things that fit this. I mean, just about everything. Area of rivers, population, constants, newspapers, specific heat, pressure. I don't even know what HP is. HP lost, molecular weight, drainage, atomic weight, the reciprocal of n and the square root of n, design, Reader's Digest, cost data, X-ray voltage, American League, black body, addresses, death rate. This is just all over the map. So in other words, just pick up a book, open it up, and Benfords Law works. And they've tested this over and over and over again. So anyway, just kind of interesting, a statistical phenomenon of real data has this, once again, has this pattern to it that looks like this. And becomes kind of really a handy tool for detecting fraud. Is fraud a problem? Yeah. In fact, it's getting to be more and more of a problem. There are always a number of people who want to gain dishonestly because it's I guess they figure it's better than working, and I just find this, I don't know, thought this was really surprising. So I wanted to show you about it. Okay, sample space. Let me just remind you, I haven't really spent any time on that, but I think on the movie, she showed you the sample space for flipping a coin. Let's do a sample space for, I don't know, do we have, I guess, yeah, a simple one, a sample space for rolling a single die would be 1 through 6. 1, so what's a sample space? A sample space is where you list all the possible outcomes. Now, you want to make it a little more complicated? You say, all right, 2 shakes of a single die. So now, we're not going to have time to do the whole thing, but now we would start listing pairs of numbers. So I guess let's do it like this. There's a possibility of getting a 1, and then on the second shake getting another 1. I'm sure you can see there are different ways to organize this, but and then what? We could start going off 2 on the first, 1 on the second, 2, 2. Okay, you can imagine now how many are there going to be here altogether? Yeah, 6 in each row, and we're going to have to go down 6 rows. So 6 times 6. So this sample space has a size of 36, and that's why we could do the same thing with 1 shaking of 2 dice, right? Sample space then is your. Now sometimes, yeah. Now some of you might look at this and go, wait a minute, aren't these 2 the same? Answer that for me. Based on my formatting, are these different or are these the same? They're different, right? This one means you got a 1 on the first shake and a 2 on the second. This one means you got a 2 on the first shake and a 1 on the second. And so they really both need to be there. So we really aren't going to get duplicates here because it's important to us that we do it in a certain order. Now we could go through that and then we could say, all right, what are the chances of, and by the way, yeah, these were single shakes, right? Okay. I was just going to say, what are the chances of getting a 5? on a random shake. And now you would pick out all the ones in the sample space that have a total of 5. And there should be several of them, right? There should be a 1 and a 4. There should be a 4 and a 1. There should be a 2 and a 3. There should be a 3 and a 2. That should be it, right? There is no 0. So how many was that? 1, 4, 2 of those, 2, 3, 2 of those. Am I counting correctly? We got 4, right? What did I miss? So 4 out of 36, and then you could reduce that. So sample space, again, and you got to think this through carefully. Is order important? You know, what are the chances of just getting a 1 on the first shake and a 4 on the second? 1 out of 36. So there are differences. If I ask you for a total, then you got to look for all the possibilities. So sample space, wanted to get that topic in. And I thought we'd just go through some sample problems. So if you would turn to page 232, I picked out some even-numbered problems to work through. Get us into the feel here, and we'll get you going on the actual assignment. A company that offers courses to prepare would-be MBA students for the Graduate Management Admissions Test has the following information about its customers. 20% are currently undergrads in business, 15% are undergrads in other fields of study. So in other words, people from other fields of study sometimes still take this test. 60% are college grads who are currently employed, and 5% are college grads who are unemployed. Is this a legitimate assignment of probabilities to customer backgrounds? Why? So what do you think? Are those percentages realistic? Yeah, the first thing you got to do is see that the probabilities have to add up to 1 or 100%. Remember that? And we have what? 35, 95, 100. So that makes sense. That's the big one. What percent of customers are currently undergrads? Now, you got to be careful here. There are 2 such groups that have to be put together, right? Do you see that? It says 20% are currently undergrads in business, and 15 are undergrads not in business. So you'd have to say 35%. So there you just have to be careful that you read carefully. Let's go on to number 16. Okay, 916. Bottom of page 234, race and ethnicity. The 2000 census allowed each person to choose from a long list of races. That is, in the eyes of the Census Bureau, you belong to whatever race you say you belong to. So whatever you get this questionnaire in the mail, you check something, that's what they assume you are. Okay? Hispanic Latino is a separate category. Hispanics may be of any race. If we choose a resident of the United States at random, the 2000 census gives these probabilities. So these are numbers right from the census. Okay, so do you notice how Hispanic and not Hispanic completely crosses over the races? Okay. So verify, is this a legitimate assignment of probabilities? Well, I did a few totals. You can see, you might be able to make them out. The first column added up to 0.125. The second column added up to 0.875. And if you total those, you really do get 100%. So that makes sense. All right. And so if you showed 0.125 plus 0.875 equals 1, you've done that. What's the probability that a randomly chosen American is Hispanic? You got to just carefully read the chart. So if you randomly choose an American, what's the probability that they will be Hispanic? I know, I wrote it on there, but isn't it the total of that first column? 12.5%, 0.125. C, non-Hispanic whites are the historical majority in the United States. What's the probability that a randomly chosen American is not a member of this group? So first of all, look it up. Find the white non-Hispanics on the chart. It's the 0.691, 69.1%. Okay? If that's the probability of being a white not Hispanic, then what's the probability of not being in that group? Always principle of probability, it's 1 minus that, right? So 100% minus 69.1% would be what? 30.9%? Is that it for that one? I think so. Yeah, stop me if you have any questions on these. Number 20, grades in an accounting course. 20. So this one is found bottom of 238, top of 239. North Carolina State University posts the grade distributions for its courses online. Students in Accounting 210 in the spring 2001 semester received 18% A's, 32% B's, 34% C's, 9% D's, and 7% F's. Choose an Accounting 210 student at random. You know what that means. Give every student an equal chance of being chosen. The student's grade on a 4-point scale, A being 4, B being 3, C being 2, D being 1, F being 0, is a discrete random variable of x. The value of x changes when we repeatedly choose students at random, but it is always one of 0, 1, 2, 3, 4. Here's the distribution of x. Well, first of all, does that match? Get this language down. What you see down here, does that match up with the paragraph up here? They call this the distribution of x. It's the probabilities laid out. Once again, the sum of these 5 possible outcomes, there are only 5 possible grades you can get. 0 through 4 on a 4-point scale. The sum of those should be 100%. Let's just check it. 16, 50, 82. Yep, that adds up. Do they match the numbers up here? Yeah, they've just been changed to percent form. So 7% has been changed to 0.07. Okay. A. Say in words what the meaning of is. I purposely didn't read it because what does this thing in the rectangle say? How do you read that? Right, the probability that x is greater than or equal to 3. What is this probability based on the distribution? What are the chances of getting, what does that mean? What's the probability of getting a C or above? No, a B or above, excuse me. And what is it? The sum of these two. It's either the probability of getting a B or the probability of getting an A, and that's the sum of the two. So you got a 50% chance in that particular class of getting at least a B. Okay, write the event, quotation marks, the student got a grade poorer than C in terms of values of the random variable x. Well, I've written this one down. So I said P, probability, that x is, it said poorer than C, So just less than 2. And what is it? What is the probability that you're going to be less than 2? Well, these are the only 2 that fit that. So it'll be the sum of these two, 0.16. So you're going to be asked to interpret writing like this. And you may have to actually write some of these statements yourself. Get used to that P notation, okay? Okay, P22, or problem 22, 922, sorry. I'm on P's now. Iowa test scores. The normal distribution. I don't know. Did any of you used to take Iowa tests? Yeah, a bunch of people have used those. It was a very commonly used achievement test. Normal distribution for Iowa scores with a mean 6.8, standard deviation 1.6 is a good description of the Iowa test vocabulary scores of 7th grade students in Gary, Indiana. If we use this model, the score y of a randomly chosen student is a continuous random variable. And he said the figure is on page 57. I decided to put it right on here to be more convenient. Okay. So hopefully you can see that well enough. It says, write the event the student chosen randomly has a score of 10 or higher. So that would be what? P, x is greater than or equal to 10. Close parentheses. I should write that up here. Except it was y, isn't it? And then it says, find the probability of this event. Okay. Well, the score, as you can see, is down on the bottom. Now we have nothing. I should check on 57. Did I cut off a scale? I don't think I did, but let's just take a look. 57. Nope, that's it. That's the whole graph. Okay. So, score of 10 or higher. So, I gotta just see, how does the beginning of that graph look? Just nothing below 2. So 10 or higher. Hard to tell the counts, isn't it? I gotta think about what I did on this one. Because these are supposed to be counts. Anyway, it would be the sum of these 3 areas divided by the sum of all of them, right? And let's just what am I missing? What's that? Still not hearing you.
Can you find the C-score?
We do know mu, we do know sigma. So, right, thank you. So we got to just think normal. We can't do a count here, and that's why we don't have anything on the scale. So we take our score of 10. Now, you've got to remember, though, everything in the table is going to be left. So what are we going to have to do? Subtract from 1. So what you're going to do is take 10 minus 6.8 divided. We got to do our z guy. So score minus mean divided by standard deviation. And what is that going to give us? 3.2 over 1.6, which is exactly 2. Hey, we don't need the table this time. If it's right on one of those, can't we use the 68, 95, 99.7? Okay, between two either way is 95. So what does that leave for outside on both sides? 95, everything else would be 5%, but I only want the top end. 2.5%. Does that make sense? So, and the answer using your table will be just slightly different, but let me just go through that again. 68% is within one either way. 95 is within two either way. 99.7 is within three either way. Well, we have the two here, so 68 and 95. But I don't want to know what's in here. I want to know what's up here. Well, if 68 are in here, if 95 are in here, that leaves 5%. Equally balanced. I only want this, so half of 5% is 2.5%. Okay. It's been a while since we've used that law. All right, this one's pretty simple, but you're going to get some of these. Land in Canada. Statistics Canada says that the land area of Canada is 9,094,000 square kilometers. Of this, 4,176,000 square kilometers are forested. So if you chose a square kilometer of land in Canada at random, what are the chances you would choose one that's forested? Well, it's just what? The 4 million number divided by the 9 million number. 45.9%. What's the probability that it's not forested? 1 minus that. So there's no mystery here. We don't need any tables. The numbers are all right in front of us on this one. Okay, how about this one? Number 28. Page 242. Foreign language study. Choose a student in grades 9 to 12 at random and ask if he or she is studying a language other than English. Here is the distribution of results. Okay, so 59% of the students are not taking a language other than English. Is it a legitimate probability model? Well, is the sum 1? 35%, 38, 41, 100. Yeah, it's legit. Second, what's the probability that a randomly chosen student is studying a language other than English? I just asked you that. 1 minus 59%, right? Or you could add up Spanish, French, German, and others. And both ways you should get 0.41 or 41%. What's the probability that a randomly chosen student is studying French, German, or Spanish? Well, that would just be the sum of those three individual probabilities, and that would be 0.38. Another one, 930, colors of M&Ms. If you draw an M&M candy at random from a bag of the candy of M&Ms, the candy you draw will have one of 7 colors. The probability of drawing each color depends on the proportion of, I'm amazed that somebody sat and figured this one out, but anyway, here's the distribution. As you can see, they're not all equal, are they? And in fact, one is missing. So the question is, I know I got the answers up there, but what must be the probability of drawing a blue candy? Well, you take a look and add up what you've got there, and you already have 0.9. And if this is a true probability model, and all are represented, then blue has to be 0.1, right? So that they add up to 1. What's the probability that you do not draw a brown? 1 minus 0.1. What's the probability that the candy you draw is either yellow, orange, or red? Again, the key word or. So yellow, 2%, 20%, orange, 10, and what was the other one? Red, 20. Altogether, doesn't that total up to 50%? Let's see, should we do this one? Yeah, let's take a look at this legitimate probabilities. This is number 32. In each of the following situations, state whether or not the given assignment of probabilities to individual outcomes is legit or not. So when a coin is spun, the probability of a head is 0.55, and the probability of a tail is 0.45. They didn't ask you if it was a fair coin. They're just saying, is that legit? The answer is yes, because 0.55 plus 0.45 truly is 1. B, when two coins are tossed, the probability of both heads is 0.4. The probability of a heads and a tail is 0.4. The probability of a tail and then a head is 0.4. And the probability of a tail and then a tail is 0.4. Well, you got what? Way more than 1, right? 1, 2, 3, 4. 1.6 for a total. No go. When a die is rolled, the number of spots on the up face has probability of a 1, 1/2, probability of a 4, 1/6, probability of a 5, 1/6, probability of a 6, 1/6. Well, we got to do a little adding here. 1/6 plus 1/6 plus 1/6 is 3/6 or 1/2. Yeah, this works. It's a weird, it's a strange die. It's obviously loaded, but from a probability standpoint, this makes sense because they total 1. I guess we're out of time here. Got a roulette one. So, next time, 1 to 51 odds, but I already told you, what is it, 23 I told you to skip? Is that right? 1 to 51 odds, but not 23. Good to have you back. Hope you had a good vacation. See you on Wednesday. Oh, yes. He is a nut, isn't he? It's amazing how much of that makes sense to Luther. You know, like all the potluck jokes. Oh, that's a good one. All the kids are above average. Last time they saw a movie, and in the movie, I don't think you saw that, but in the movie they said they asked people, they just went and randomly asked people on the street, are you above average driver? And everybody said yes. Yeah. And then they said, this can't be. You know, we got a little problem here.
But it's good they feel good about themselves.
Yeah, at least that's right. We achieved a positive attitude.
That's right.
Of course, I don't know how good it is if everybody thinks they're wonderful drivers. That could create problems.
That's scary.
Yeah. And one guy that, by the way, they asked had a cast on, and his buddy did too. And they asked him, "Are you above average?" "Yeah, I think I am a little above average." And his buddy that was there said, "He's not above average. Take a look at him." That was really funny. Yes.
I was wondering if there's any way that I could change the time that I take my final exam for this class.
Probably.
Because I have 3 in a row straight that
Oh,
day.
that's no good.
No.
Yeah, I'd be willing to do that.
Okay.
Why don't you think about a time and just let me know. I'm probably going to be here, and so I don't have a problem with it.
Okay.
So you can, why don't you tell me what would be best for you?
Because I was thinking sometime that Wednesday. I'm free anytime, so.
Would you prefer morning?
Probably, yeah.
So Wednesday morning? Okay. All right. sounds good. Let me just take a look at what, see what I got here. Maybe I can look right now. Yeah, I don't have any that day.
Okay.
So what time would you like?
What time is the first session for exams?
8 o'clock.
Sure, I'll do that. Should I just come in here or go to your office or?
I would say come to my office.
Okay.
We may have to figure out, I can't tell you offhand what room's available. We'll just
Okay.
find you a nice quiet place.
Okay.
8 o'clock Wednesday, and that's December 12th. And that's the 117th.
Thank you very
Okay.
much.
You're welcome. 3 in a row.
Yeah.
Is not good. When you say in a row, you actually mean consecutive exam time slots?
Yeah.
Oh
Makes
my.
the chat going.
Isn't that wonderful how that worked out?
Yeah.
Oh, so they left you a little time to pray in there.
Yeah. Thank you.
Yeah.